Ugh, oh, my writing went away again. All right, so we had 8 pairs. Sorry about that. Okay, so carbon's going to be an central, and then it's going to be just surrounded by the oxygens. I just put them at 9 and 3 o'clock just because I felt like it. Okay, now with the 8 pairs of electrons that we have available, we know carbon is our least electronegative, so it'll be surrounded by the more electronegative oxygens. By distributing the electrons, the most electronegative entity gets first dibs, if you will, on the pairs of electrons. So that means I am going to say, okay, a single line represents a pair of electrons. It also represents that the carbon and the oxygen are sharing a pair of electrons. There's pair, one pair, 2 pair, 3 pair, 4 pair, 5, 6, 7, 8. Okay, so some of these are a little hard to see. Here we go. There. Okay, so each oxygen has 4 pairs of electrons. The 4 pairs they have are 1 bonding pair and 3 non-bonding or lone pairs of electrons. Now, the problem we have here is we're not done because carbon does not have an octet. Okay, an octet means carbon has 8 electrons surrounding it. Right now, it only has 4. 2 from this shared bond and 2 from this shared bond. So carbon needs 4 more, but we've used up all the pairs of electrons. So what we can do is we can say, okay, let's go ahead and share more than just 1 pair of electron between carbon and oxygen. So these will go away and a double bond will occur between the carbon and the oxygen on the right. The same thing will happen with the oxygen on the left. So in the end, what we will have is this. Okay, we will have a carbon that is sharing with oxygen 2, 4, 6, 8. That means carbon is good and it has a total of 8 electrons and its octet is satisfied. Oxygen, each one, has a total of 2, 4, 6, 8 electrons shared as well. So it too has an octet. The other oxygen does the exact same thing because they're identical. Now, that's getting the main structure. Now we're going to talk about 2 other topics. The shape, what the names are, and also if there is any polarity overall in this shape. Now, when we talk about shape, I also uploaded a tutorial. Oh, I can't remember if I put in the 7, 9, or 8 helpful information chapters, but it's called VESPR, V-S-E-P-R, and other documents are called electron configuration. Those are your shapes that you have to know and memorize. Okay, we are going to talk about both molecular structure and electron pair geometry for the 2 different types of shapes that we can get from different molecules or different compounds. So first and foremost, this shape is what we call linear. Okay. It is linear because literally it takes on a 180-degree angle between the carbon and the oxygens. There's no bending and there's no need for anything to repel itself. Remember, those oxygens have 2 non-bonding pairs of electrons, and those electrons, because they are like charge, they are both negative, they want to be as far away from each other as possible. And so we get this linear shape. Molecular shape in this regard is the same. It's also linear. The difference between electron pair geometry and molecular shape for shape is electron pair geometry takes into account any lone pairs on the central atom, and molecular shape does not. And you won't see that in this example, how they're different and where the differences come in, because there are no lone pairs of electrons or non-bonding pairs of electrons on the central atom. Okay, so this is linear. The next thing I'm going to look at is it polar? Is there a dipole moment anywhere? When I'm asking if it's polar, what I mean is, if you can imagine a seesaw, if there's two equal weights on each end, it will be perfectly linear, just like you see here, meaning there's not a pull in one direction or the other. If I put an adult on one end of a seesaw and a 2-year-old on the other end of a seesaw, there's going to be a clear difference in strength on who holds that end, their end down. Okay. Now, don't get me wrong. It's not like this is going to tilt left and right because it's linear. I just want you to think in your head about relative strength. So again, going back to electronegativity, oxygen, we said, is 3.5. Carbon is 2.5. Okay. Now, the difference in electronegativity between these two is 1.0. Our rules are, if the electronegativity difference is less than 0.5, it is considered nonpolar. Okay. If it's between 0.5 and 1.7, it is considered polar, covalent, nonpolar covalent, and polar covalent. And then anything greater than 1.7 is considered ionic. Okay, so the bond between the right oxygen and the carbon is a polar covalent bond. That would also be true for the one carbon on the left. It is also an electronegativity difference of 1.0. So what that means is each oxygen, even though they're sharing their two pairs of electrons with carbon, the pull of those electrons are closest to the oxygen. Okay, what does this mean? Well, pretend I'm playing tug of war. I'm playing tug of war with a 2-year-old. Now, we are still holding that rope. We're still holding it. We're still sharing it, one of us on each end. But if we both start pulling, I am stronger than the 2-year-old. I'm going to pull that flag closer to me, even though we're still sharing the rope. That's what's happening with carbon and oxygen. And when these little symbols I did were deltas, the delta symbol with a negative and delta with a positive, that means there's more electronegativity on the oxygen end because those electrons are being held closer to oxygen. Okay. Now, the oxygen on the left is doing the exact same thing. And it is doing it equally. So while we would say individually there is a pull in one direction versus the other, overall there is no overall pull because both the left and the right side negate each other and cancel each other out. So overall this compound is nonpolar. Okay? Let's talk about CH4. We're going to do the same thing. We're going to say carbon has 4 valence electrons, and there is one of them. Remember, I'm getting valence electrons right from the periodic table. Carbon is in group 14, therefore it has 4 valence electrons. Hydrogen has 1 valence electron, but there are 4 of them. So we have a total of 8 valence electrons. Divide by 2, this gives us 4 pair to go around. Now, our central atom is always the least electronegative, but never ever hydrogen. So our central atom here is carbon, and hydrogens are going to surround it. And I'm just doing a raw sketch here at 12, 3, 6, and 9 o'clock. okay? Now, because there's 4 pairs to go around, and carbon gets first dibs on the pairs because carbon is most electronegative here, we're going to say 2, 4, 6, 8, okay? Carbon has an octet. It is sharing 4 pairs of electrons with each hydrogen. Hydrogen is an exception to the octet rule. Hydrogen not only does not need 8 electrons, it doesn't have anywhere to put them. Hydrogen only has a 1s energy level. There is nowhere to put 6 other electrons. It's like saying I want to put 8 people in a 2-seater car. There just aren't any seats in a 2-seater car, so 6 more people cannot fit. Okay, so hydrogen is is our first exception we're going to talk about for the octet rule. Carbon is not. All nonmetals except for hydrogen must have an octet in one way or another. So this is going to be our generic rough sketch shape. What this actually looks like is this. Okay, this is what this actually looks like. And the reason for this is because of repulsion, which we'll get way more into in chapter 9. This is our tetrahedral, well, for molecular shape and electron pair geometry, it is the same. These are tetrahedral. They're the same because there are no lone pairs of electrons on the central atom to take into consideration for electron pair geometry. So both the molecular shape and the electron pair geometry shape are the same, both tetrahedral. Now the question is this polar or nonpolar? Well, let's look at the electronegativity values between carbon, which is 2.5, and hydrogen, which is 2.1. The electronegativity difference between these two is 0.4. That is less than 0.5, so each carbon-hydrogen bond is nonpolar covalent. Okay? Because each one is nonpolar covalent, overall, there is no pull in any general direction because they're so close to even in strength, they're both holding on to those shared electrons pretty evenly. All right, so let's think about that just generic every day. If I have 2 2-year-olds, they're not going to have an equal strength unless they're identical in every way, shape, or form, but they're relatively going to have the same strength of most 2-year-olds. They're going to pull on to that rope pretty evenly between themselves. Okay, so overall, CH4, carbon tetrahydride, is nonpolar. Okay, but I want to switch this up a little bit. I want to say, well, what if we didn't have hydrogens here? What if these were fluorines? Okay, what if they were fluorines? We would still have a tetrahedral shape, but now we would not have you know, an instantaneous, oh, just look, you know, it's got to be the same. It's got to be nonpolar. Carbon is 2.5, like we said. Fluorine is 4.0. Okay? So the difference here is 1.5. That is very, very close to ionic. Remember, we said anything over 1.7 and the electronegativity difference was considered ionic. So this is each carbon-fluorine bond is a very, very strong ionic bond, polar covalent bond. It's a very strong polar covalent bond. The problem is, much like carbon dioxide, they are all exactly the same at 1.5 difference, so they all cancel each other out. And overall, even CF4 is non-polar. Okay? So here's one last caveat to this. The only way this structure could be polar is if the attachments were all the same except for one. So perhaps I have hydrogen, 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 and oxygen. Oxygen is 3.5. Carbon is 2.5, so the difference is 1. So there is an overall dipole moment in the direction of the oxygen. Because it's more electronegative, that means it's stronger. That means it's holding its shared electrons closer to itself. So now we're going to talk about water. Oxygen has 6 valence electrons. Hydrogen has 2, and there are 2 of them. So that's a total of 8 valence electrons, which means 4 pairs to go around. Okay, oxygen will be our central atom because although it is the most electronegative here, hydrogen can never be the central atom because it can never have an octet. So the hydrogens are going to go on the outside and surround the oxygen. So first dibs on the pairs is oxygen, 2, 4, 6, 8. Okay, those are our 4 pairs. We have here 1 pair, 2 pair, 3 pair, 4 pair. So those are our 4 pairs. And the problem is it actually doesn't take this linear shape on like carbon dioxide does. And the reason for that is because of these lone pairs. These lone pairs are trying to not only repel each other, but also attract to the hydrogens, and the hydrogens are also trying to repel each other. So when we have 2 bonded things and 2 sets of non-bonding or lone pairs of electrons, what we actually get is this shape. And this will be the first time in the examples where we will have a different name for the molecular shape and the electron pair geometry shape. Okay, the molecular shape is simply, we call it bent. Okay, it's bent when you have 2 attachments and 2 sets of non-bonding electrons. All right. Electron pair geometry, if you remember, we said does take into account any lone pairs of electrons that are on the central atom. So these electron clouds from the lone pairs of the electrons make it appear as if oxygen really has 4 attachments. What we actually have here are what we call 4 electron clouds, meaning 2 actual attachments of the hydrogens and then 2 non-bonding. So this will also be tetrahedral, just like CH4. Okay. Now, the question is water polar or nonpolar? The electronegativity difference between the hydrogen and the oxygen is 0.9. So hydrogen is 2.1. I said 0.9. I meant to say 1.4. I'm sorry. And oxygen is 3.5. Math is hard today. So the difference here is going to be 1.4. So what we have is the least electronegative is still sharing with the most electronegative, but those electrons are being held more closely to oxygen, okay, in both cases. In addition to that, there are lone pairs of non-bonding electrons on oxygen, which I almost think of it as like a booster, okay, like a booster, turbo booster, okay, they just give way more electronegativity. So there's an off balance here of electrons and negativity versus positivity. So we get a dipole moment in the direction of the oxygen. There is a dipole moment. Ugh, I can't spell today either. And it is in the direction of the oxygen. What that means is that there's an uneven pulling of electrons by oxygen, making oxygen more electronegative than the hydrogens, which are electropositive, more so, because oxygen has a stronger electronegativity. So we have a partial positive and a partial negative end for oxygen. Now, I keep saying the word partial, partial, partial. This is because unlike, for example, sodium ions, when they become a cation, they have a full-on charge in and of their own right. They've lost entirely an electron. Nothing in water has gained or lost electrons. It is just sharing them so unevenly that hydrogen feels like it's partially positive and oxygen feels like it's partially negative. I can't believe I just did that again. I'm sorry. I'm just going to write these shapes again really quick because we got to talk about polarity. Okay. All right. So here is the shapes again. Now, if you can hear that snorting, it's my bulldog sitting below my legs, trying to sleep, but he's very obnoxiously loud. I am sorry about that. Okay, so polarity, what's going on here? First things first, the bonds between nitrogen and hydrogen, nitrogen is 3.0, which I'm getting right from my electronegativity chart, and hydrogen is 2.1. So we get a difference here of 0.9, and that is polar covalent. And each one is polar covalent, okay, in the direction of the nitrogen. Nitrogen also has those lone pairs of electrons, which is an even added booster. So we get a dipole moment in the direction of the nitrogen, and it is in fact polar with a dipole moment present. BF3, I'm going to give you a rule to memorize. This is nonpolar. And the reason for that is twofold. One, it's trigonal planar. Okay. And two, all the attachments are the same. And because they're all the same, they all cancel each other out. There is no lone pair of electron here to do anything, to boost anything. When you have a trigonal planar, meaning no lone pairs on the central atom, and all the attachments are the same, it is always and forever nonpolar. Memorize that and move on. Don't know why my computer keeps doing this. I apologize. Even though there's a pull from of the electrons towards oxygen, these lone pairs of electrons on sulfur are the booster. They hold more electronegativity than the pull of the sharing of the oxygens towards them. Therefore, sulfur is polar, but it's in the direction of the sulfur, not the oxygen, because of those lone pairs of electrons. Okay? Now, let's just talk about one thing. What if this wasn't SO3 2-? What if this just was SO3? Okay? If you remember, SO3 2- gave us 13 pairs of electrons because we had 24 plus we had to add the 2. So we know that this SO3 has 24 pairs of valence electrons. So dividing that by 2 gives us 12. Okay, 12 pairs. So what we would actually see here is this, just like we saw before. Here are the 12 pairs. The problem is sulfur does not have an octet, and all non-metals must have an octet. So what do? What we do is these go away and a double bond is formed. Okay? And that's because they're going to share more than one pair. Now, the question you might ask is, does it matter which oxygen we do this with? And the answer is, great question. No, it doesn't matter. So I could have it look like this, or I could have it look like this. And they are all correct because these are what we call resonance structures. Okay, these are resonance structures, meaning due to stability and to electron movement, this sulfide ion is constantly switching those double bonds between the oxygens. It's always happening. So what we do and how we represent that, this is each resonance structure. This is structure 1, this is resonance structure 2, this is resonance structure 3. Okay, so how we write this so that we can kind of figure out what's going on is there's one simple way we write it to show that it has resonance. And the way we do that, hold on, I'm trying to see if my pen has options. It does not. Okay, the way we do that is we draw the second double bond as a dotted line on each one. And what that tells us is that this double bond, there is one double bond there, but it floats between the 3 oxygens. Okay, that's how we represent that. Now, if we're going to talk about the shape here, for this particular one, our molecular shape is trigonal planar. And because it is trigonal planar, it is non-polar. It is trigonal planar and all 3 attachments are the same. Therefore, it is non-polar. Okay, so P2F5. There's not going to be a whole lot of things we're going to talk about where there's more than one central atom. I'm going to limit a lot of that because if you're going to go on to organic 1 and 2, that's really where you're going to get into the majority of that. I just want to introduce this topic to you a little bit. So again, like we said, least electronegative would be the central, and most electronegative would be surrounding. Phosphorus is 2.1 and fluorine is 4.0. So that should tell you that phosphorus should be the ones in the middle, and they will be surrounded by fluorines. Okay, and I'm not going to get into how and why and where. I'm going to save that for organic. But this is how you should understand that the least electronegative would be going in the middle. For example, if I had C2H6, carbon is more electronegative, but hydrogen is never the central atom. So it would be carbon-carbon, and then the hydrogens surrounding it. Okay. I just want you to have that basic understanding. All right, that is it. Check. Yep, I'm pretty sure this is it for all the examples we've done. I will upload this PowerPoint, and then you'll have it handy. And if you have any questions, let me know. Thanks. See you next time.